welcome everyone to this latest Zero Carbon Mine webinar. Today, we're talking about innovative carbon removal technologies. We've got Tamsin from ARCA Technologies, and we're meant to be having Andrew Pedley from Carbonaut, but he's having a few troubles dialing in, so hopefully we'll have him online soon. So I suppose we try to keep these sessions fairly casual. So if you've got any questions as the presentations go through, then please put them in the Q&A, and we'll try to get them as we go through. But without any further ado, I'll hand over to Tamsin to start, running through her preso. Thanks.
Oh, thank you very much. Let me just see what we've got here. Okay, are you seeing my shared screen? Are we seeing
Yes, we've
that?
got that.
Oh,
yep.
That's great. Okay, thank you very much, Brett, for asking me to join your fantastic webinar. And it's lovely to see some familiar faces of people that have joined, so thank you very much. Today I'm joining you from Perth. I'm not sure where everybody else is, but I'm in Perth, WA, on Noongar country. And in my presentation today, you're going to see quite a few pictures from our site trial, and that is on Shawal land. Today, what I'd really like to do is let you know who we are at ARCA and what it is that we do. So our mission is to restore the Earth's atmosphere by returning gigatons of carbon dioxide to the ground where it originally came from. We do this by capturing atmospheric carbon dioxide and transforming that into rock, where it's stored safely forever. At ARCA, we partner with mining and energy companies to repurpose their mine waste for industrial scale carbon dioxide removal. So let's just have a quick look at the problem that we're trying to address here and eradicate if possible. The Paris Agreement states that in order to meet our net zero emissions targets, we need to limit global warming to 1.5 to 2 degrees C by 2100. We know already that the emissions reductions alone is not going to be able to let us meet this target. So what we've got to do is actively capture carbon dioxide in a process called carbon dioxide removal, or CDR, and take that out of the atmosphere. But how much do we need to take out? That's always the big question. I went and had a look online, and I found the State of Carbon Dioxide Removal report, which was co-authored by the University, or Oxford University, in 2024. And they stated there that we need to remove between 7 and 9 billion tonnes of CO2 annually from the atmosphere to be able to meet these goals. Those are pretty lofty goals and mega amounts of CO2 that we need to remove. So in order to remove those types of levels of CO2, we need to be looking at industries that are generating lots and lots of waste, or moving lots of pieces of agriculture. So the big things that are being used really on the industries that are being used for prospective CDR are the mining and agriculture areas, just because they generate so much waste. And when we look at mining, we're really only looking at a fraction of the ore that we're keeping as part of our product. So we're generating a large amount of waste. So we need to do better with those waste streams. I'm not sure sort of where everyone has come from, so I thought I'd just quickly touch on what is the process of carbon mineralization or mineral carbonation. I tend to use these phrases interchangeably, and it's a naturally occurring weathering process. So let's have a quick look at this diagram. You can see that what we're doing is we're using minerals. These minerals are quite high in calcium and magnesium. When they go out to the tailings dam, they go out in a slurry form very often. And so they're in a watery environment. And that watery environment is really important for mineral carbonation because it's where all the reaction takes place. So in that water, we've got air moving in and out of that moisture layer, and carbon dioxide dissolves into that and forms a hydrogen carbonate surrounding the mineral. We also see calcium and magnesium ions being liberated into that particularly water area. And when the two ions combine, the magnesium and the calcium combine with the hydrogen carbonate, we form a carbonate mineral, which can cement together to form sort of quite a hard crust on our tailings dam. So ARCA was co-founded by Professor Greg Dipple from the University of British Columbia. He's a world-leading researcher in carbon mineralisation of industrial waste, and he's been working in this space for over 30 years. Some of the early work that Greg was doing involved going out to mine sites and looking at some of the crusts that were being formed there, and he realised that passively, some of these tailings were capturing carbon dioxide, albeit quite slowly. So the question he and his team were asking is, what can we do to increase these rates of carbon mineralisation? And is there any way that we can commercialise that? So ARCA was set up, and what we've done is we've developed the technologies to be able to accelerate and measure the process of carbon mineralisation, but also to be able to measure how much carbon dioxide it is that we're capturing. So here's an overview of our technologies. Let's first have a look at the waste that we can use as feedstock. When we mine ore bodies, there's a lot of waste rock that's generated. That is a potential source of a feed for carbon mineralisation. Also, within the mining process and processing circuit itself, there's often a midstream that's generated. We could possibly use that as well. And most certainly at the end, in the tailings that is generated from the mining, we can definitely use that. We have an activation technology that's positioned really for going in line post-processing and going out to the tailings dam. So somewhere in that stream there. And what that does is it activates the feedstocks that we're looking at to increase their reactivity. Our third piece of technology is our smart churning technology. And what we're looking at there is once the mineral and the waste has actually been deposited into the tailings dam, we send out our rovers, and this is able to manipulate the tailings to promote carbon mineralisation. And of course, once we've promoted it, we need to know how much we've captured. So we have something called MRV technology. And MRV stands for Monitoring, Recording and Verification. There's a lot of acronyms in the CDR space. Again, another one, carbon dioxide removal. And what the MRV technology does is it allows us to quantify and validate, importantly, how much carbon dioxide has been captured. So let's have a look at these sort of individually. We'll start with the MRV technologies. Over the past year, ARCA has been working with Isometric and a number of other professionals in this area to develop an ISO accredited methodology for measuring carbon dioxide captured, through our processes. This is very important as the MRV process for us determines how many tonnes of CO2 we've captured and therefore how many tonnes we can offset or our contributors can offset, or alternatively, how much we can sell in the voluntary market. So this little bit of kit is actually, it's called an eddy covariance tower. We place it out in the middle of the tailings dams. It sits about 2 metres high, and essentially it's like a little weather station. And what it does is it is able to read the composition of the air sort of for 200 metres in front of it, and as that air approaches the eddy covariance tower. And more importantly, what it does for us is it reads the changes or the flux in the carbon dioxide component of the air as it moves across the tailings. This allows us to estimate and model how much CO2 has been captured as that air moves across the tailings. And that gives us one set of readings. This is a modelled set of readings. Now, our second little tool in our toolkit is called dynamic closed chambers. And these are actually able to measure the CO2 that's captured. And in this beautiful photograph, you can see Beatrice, and she's standing out in our TFF. And next to her is a yellow box, and next to that is sort of a white dome. That white dome is actually the dynamic closed chamber. And what it does is it's connected to the yellow box, and inside the yellow box is the monitoring device that is able to record CO2 in air. When we go out to site, we distribute and place out in the field a number of collars that stay there for quite a long period of time. When we walk out, we take out these little dynamic closed chambers and the yellow boxes that go with them. We place these over those collars at all of these different locations. And when we close the dynamic closed chamber, the dome lowers over the collar and captures a known volume of air. And what we do is we measure the change in CO2 composition in that air under that dome over a 90-second period. And what that tells us is we can see that CO2 level dropping. And so we're actually able to see carbon mineralization taking place in real time. And that's very exciting for us. So that's the second measurement that we will take out in the field. Our final sort of piece of this puzzle is our third form of measurement. We've developed novel ways to deploy MRV technologies, and what we use here is our amphibious electric rover. And this allows us to access areas of the tailings that might be too damp and that we're unable to walk on. You'll see that it's got these little scrolls, these shiny aluminium scrolls. They allow the rovers to float if need be. And what we can do is we can deploy those rovers out to go and take samples, physical samples of material that's been mineralized, so that we can send that off for assay, so that we get our third layer of measurement. This all provides us a lot of confidence in the data that we're collecting. So one of the first things that we can physically do to increase the rate of mineral carbonation is smart churning. And again, we'll use our rovers here. And in this photograph, you can see from site, when the tailings are deposited, they're really smooth. That's sort of in the background of that photo. Where our rover has passed over, the whole area is looking, it's all churned and it kind of looks fluffy. And what essentially our rover does is it increases the surface area of the tailings dam. And it also, we found that what we need is an optimum level of moisture to be able to allow that mineral carbonation to take place really effectively. And that is quite different for each of the samples that we look for, or look at, sorry, and that can be based on mineralogy, pH, grain size. But what we can do with our rover is we can control the moisture content, either by bringing up moisture from underneath the surface when we churn, or if we've got too much moisture, increasing that surface area helps with rapid evaporation. Here is the data that lets you see really what happens when we churn. Okay, we've got a curve here, and running along the x-axis, we've got days from 0 to 30. So it's a 30-day reading that we're looking at here. And our y-axis shows the cumulative carbon dioxide that's been captured over that period. We measure that as tonnes of carbon dioxide captured per hectare. We've got 4 lines really on this curve. The bottom or baseline is the black line, and that really shows us what is happening naturally in this particular sample of tailings. So it's ultramafic and mafic tailings that we're looking at here. We can see that there is some carbon capture, although it's quite slow. The next 2 lines, the yellow and the green curves, the yellow curve shows us what's happening using the eddy covariance tower. That is that 2-metre tall sort of weather station. And you can see that we're getting much higher levels of carbon dioxide captured, and that matches quite closely with the direct readings that we're getting from our dynamic closed chambers, which is illustrated here by the green line. It's nice to see that we've increased the carbon capture by 10-fold, but also you can see that those 2 forms of measurement are quite closely correlated and they've got good agreement. So that gives us confidence in our data. And then I wanted to show you sort of some of the outliers that we see. I think I mentioned we deployed a number of collars across the tailings dam, and we find that we have some that are super performers, and our blue line here is illustrating one of our super performers, which is 20 times over the baseline. various things can change this and affect the performance of a particular collar space. And it might be located near a bund, so it gets more or less air moving over it. It might get more shade or more radiation from the sun. So all of those things can adjust the readings. And again, those yellow and green lines are showing us a mean. So that's across the full tailings dam. Smart churning will always be an important and useful tool for us because it allows us to optimise our in-field conditions to achieve the best possible mineral carbonation rates and carbon dioxide capture. So that's what we've got deployed, but what's coming through in our new developments in our R&D? Well, for a number of years, we've been working on ways that we can really increase the activation and activity and reactivity of the ultramafic and mafic samples. We are also looking at other ores, but we have tended to focus on these particular types of minerals in the past. So what this curve shows is the way our developments have worked over the past few years. We use microwave technology, and that emits short, sharp bursts of energy, which target the water molecules in hydrosilicate minerals. So you can see that with no activation, we've got very little carbon being captured. Then in 2023, we had some of our first carbon captures, and we were getting an increase of, say, 18-fold. With increased work and more finessing of the technology, we're finding that we're now up to 140 times what the baseline reaction is. So when we use our microwave technology or our activation technology, what it does is it increases both the rate of carbon capture, but also the capacity of the mineral to be able to store carbon dioxide. So we're very happy with that. We're working on larger bench scales and also prototypes so that we can be looking at deploying this in the not too distant future. So those are the technologies, but what about the supply? Feedstocks really is an issue. We need to make sure that we're getting enough people involved and wanting to investigate their feedstocks. So we do have quite a lot of feedstocks that are available here, and this is explained sort of graphically in this particular graphic. If we have a look at the darkest little section, that represents 1.2 gigatons of suitable fresh ultramafic and mafic rock that's currently generated. Now, if we look at deploying all of our technologies, we think that we can get 31% carbon dioxide saturation. So that small area, or that 3.1 gigatons, represents about 1 gigaton of CO2 that can be captured annually. The next sort of layer around that sort of more yellowy grey boulder, for want of a better word, estimates the one-off historical mine waste that has been gathered since we've been doing some mining and what's left on surface. It's about 28 gigatons of suitable material, which represents 8.7 gigatons of CO2 storage potential. And that's all enveloped by this large sort of bright yellow area. And this is a huge change. And what we're currently producing, which is that small grey little circle, this large yellow mass is what we're estimating, or what is estimated that we were going to need to be producing as far as tailings is concerned to meet the demand for metals by 2040. So it's a huge increase, and that will equate to about 10 to 20 gigatons of CO2 captured per year. Significantly more than the required 7 to 9 billion tonnes that is estimated from that study by Oxford. So how can our miners get involved, and what can we do to help out? Well, really understanding our tailings is vital. It's really good to have a good idea of your mineralogy, particularly any of your calcium and magnesium minerals. Getting an idea, if you can't get all of the mineralogy on that, having assays for the calcium and magnesium content is helpful. And if you think you might have something interesting, please reach out and talk to us, and so we can have a look at some of your data potentially, or have a look at your samples. And I just wanted to also stress that today whilst I've talked about mafic and ultramafic feedstocks, there are many other types of ores that are suitable for carbon mineralisation. And these include kimberlite tailings, komatiitic tailings, asbestos, steel flags, interestingly fly ash, and potentially red muds. So I'd like to thank you very much for your time, and I'm happy to answer any questions that you have. Cheers.
Thanks, Tamsin. It's very huge potential there. I'm curious, like, where have you been testing this technology so far? And I suppose what are the best sort of, the low-hanging fruit? What are the easiest sort of places to be, deploying? Most prospective, I suppose.
Okay, well, what we've been, I think, we've got it on our website that we have done a pilot trial out at Mount Keith in Western Australia. So that was an 18-month trial, and we're kind of getting to the end of that right now. That has been fantastic for us because, it's a very large tailings dam, firstly. So we were able to have a good go of it and really see what was happening there. But there's quite a lot of other mines that are available there that we could have a look at. Originally, we were really focusing on sort of nickel mines because they were really always quite obviously taking or being found in ultramafic mine rocks. But more recently, we've been looking at golds as well. And quite recently, we've been looking at fly ash and investigating the possibility of dealing with that. So it's really have a look at what you've got and let's see what we can do. And of course, you can sell those carbon credits or offset them. So we need to really start thinking about looking at this a little bit differently. It's a potential new revenue stream. So that's really exciting.
So it's quite still working out what are the best prospective sort of sites, but there's a lot of potential out there when you start, I suppose, working out what you've got to work with.
Yeah. So sorry, Brett, one of the minerals that we found that's particularly reactive is called brucite. It's not readily available everywhere. But if you do happen to have that, then that really means that we've got quite a lot that we can do without deploying too many more technologies on that. Brucite is readily very reactive by itself. More of the serpentine minerals are very interesting for us as well, but a lot of those will require activation. So, now is a good time to start looking because we're really looking at deploying that activation technology by 2027. So, when you can get some baseline work done before then.
Right. We just had a question on will the microwave technology work on dry stack tailings? So how much moisture do you need to make it work? Yeah.
Well, for the no, actually, we don't. We actually do dry our samples prior to putting it through the microwave. So you're relying on the water that is already associated within that rock itself. So the minerals go in or the tailings go in dry. So yes, it will work.
Okay. And a question around like, how do you, generating the revenue from that? Like, I suppose it's for the mining companies, it's selling carbon credits or the like. I suppose it's sort
absolutely. So there's quite a large market really in the voluntary market. So at the moment, that's predominantly being accessed really by the large tech companies. We're seeing a lot of work coming through, obviously, from Microsoft and offtakes being bought by them or credits being bought by them and sold. We're also seeing Frontier, we've got Amazon, Shopify is another one where they're buying quite readily into that market.
Righto. Yeah. So it's an emerging sort of revenue stream for the miners. Like, I suppose it's knowing what they've got there to be able to process and use this technology. It's interesting seeing like the different breakdowns, how you had, what if we do annually, the potential there, but also the historical. So, and there's a massive amount out there, and
Yeah, and I think one of the things I think is going to be quite important is, I've come from 30 years, sort of close to 30 years, 27 in the mining industry and processing. And one of the things that we really don't love really looking at is rehabilitation. The costs of that are quite exorbitant if we're going to do it properly, as we should. And, one of the opportunities that we have here is, can we use and generate some revenue from those tailings to help us really go and rehabilitate our mines, which I think is vital. And it also produces a lot of additional work for our traditional owners as well. So this is a great new sort of space that we're moving into, which I think is really exciting. And the mining industry has the opportunity right now to really make some huge differences. And instead of being, we're often sort of portrayed as the naughty kid in the class, but we can be the real heroes here and make some real changes. So I'm really excited by that.
And I also think, like, with the historic sort of mines, you probably don't really need too much infrastructure to be able to deploy this technology out to sites where there might not be too much out there at the
that's
moment,
right. I mean, we do need a couple of people, but if you have got historical mines and you've got a mine site nearby, or you're close by to a camp that you can access, then that's something that we can definitely have a look at. It's not that you need a lot of, as you say, infrastructure out there. Our rovers are battery powered, and so we can charge them with solar cells, and everything else that's out on the tailings dam, all of those eddy covariance towers, are all powered by solar energy. So we've got the full system out there. And it's a couple of people really who are operating those rovers. They're remote controlled and analysing the data. So it's not a lot, it's not a big ask as far as, employees is concerned, but also resources.
Yeah, and I suppose, so you're saying like the rovers are, they're remote controlled, but they're quite they don't. Would they get into much trouble, out on the tailings dam, or they're fairly?
They don't. We do.
Yeah.
The tailings, though, yes, they're fantastic. They are able to float. We need to be careful when we're walking out there if it's a little bit damper. So we tend to keep quite a big distance between where the rover will go if there's standing water. And we certainly stand back a lot further than that. But no, they don't get in trouble.
Yeah, they look fairly robust, and like I say, if they float and whatever, then that's helpful. Question Kingsley is saying, saying how technology looks great. Thanks for sharing. He was asking if you have a ballpark estimate of sort of costs for deploying all these sorts of systems.
That's always a good question. At the moment, we don't have one that we can sort of really share. As I'm sure you can understand, that it will be very much dependent on how, on your mineralogy of the tailings that you've got there, because that will determine how much carbon dioxide you're going to be able to capture. So it is going to be horses for courses, and most certainly it won't be particularly high, particularly if you're not looking at doing any of the activation technology at this point. But as that rolls out, it's going to be dependent on your power supply for the activation and what you're using there and the cost for that.
Right. Yeah. I think we've probably covered most of the questions. There was one around we've not recover anything from the tailings, but I think
I can address that quickly.
Yeah.
So one of the co-benefits that we think here is, firstly, when we do produce that mineralisation, it does tend to form a cement. So there are potential co-benefits, and we are investigating and getting real data on this for stabilising the TSF. And also with that, with the carbonation, you're also stabilising any potential acid mine drainage. So that is a win. As far as going through the activation process, I think that what we could find there is that, you know, if we were going to go back and reprocess, then most definitely you could recover more minerals. And in fact, the activation process could actually liberate interesting base metals for recovery.
Okay,
Thanks for that.
that's sort of a useful side benefit.
Yeah.
Just a final question before we move on is like from Sean on how the rover holds up against corrosion.
Great question, Sean. Sean and I have worked together in the past. Yes, look, we have looked at the corrosion. We're working with aluminium, and we haven't found a real issue with it, to be honest. So we have been working in hypersaline waters out there, and we have made sure that when we have done our design, the rover has been constructed with 316L, and so it is saline resistant. Of course, that's not necessarily an issue in Canada, so that they're always fun ones to address when you're moving from Canada to Australia.
Yeah. Oh, if there's nothing else, we might sort of hold the questions there and move on to Andrew to have
Thank you.
His time. But yeah, we'll hold it and see if there's any questions later on. But Andrew, if you're ready. All right. I think unfortunately we'll probably have to call time on meeting there. I think we're having a few technical issues for Andrew. But yeah, thanks everyone for tuning in. Hopefully be able to have a presentation from Andrew at another time on carbonite. We'll invite you along to that one. But we've got a couple more presentations coming up in the next month or so. A few weeks we've got one from David from SRK on how to eat the decarbonisation elephant. And a couple of weeks after that, in early June, one from ICMM on pathways to decarbonisation in mining operations. But till then, yeah, thank you everyone.